Let's explore how a generic sprite generation circuit actually works. So just as a reminder, when we develop a video core, like here, we have a couple of options. It's either a pixel generation core or a pixel transformation core. A sprite core is an example of a pixel generation core because it is generating pixels from scratch. So the focus in this video is actually not to develop the whole core, but just to discuss just the pixel generation part. So I will not be talking about how you put the wrapping circuit and how the processor actually interacts with it, or how do we actually blend it with a background image or a background pixel. So my only concern in here is like how a generic sprite core generator actually just generate these different pixels, whether that's the mouse, the ghost, or whatever shape I want to display. I just want to discuss how do we generate pixels. So the diagram that actually for that particular circuit is in here, but before I actually dig into how it works, let's just see a few things in here. So on this particular diagram in here, I'm showing you the following. So I'm showing you the full screen, basically all of the screen, and on top of it, I overlaid whatever sprite I have in here. So that sprite in here will display some sort of an image, whether that's basically the mouse pointer in here, or maybe a ghost, or maybe whatever you want to display in here. So I don't care what I'm displaying in the sprite, it's just basically a sprite. So it has a few information on it, so let's just talk about them just very briefly. So whenever we actually send the VGA screen, we actually have some sort of an XY for the pixel or the current active pixel that the VGA is displaying. So we know that this actually is doing that in here. Sometimes it's within the sprite and other times it's not. But in either cases, we have a global frame counter that is always counting, and it's generating X and Y. So I have from the global counter, or let's call it just frame counter in here, I do have the X and Y. Okay, so I have the X and Y, and again, it just represents which pixel is currently being displayed on the VGA or being sent to the VGA with the H-sync and the V-sync. I'm not going to worry about it. I just have X and Y. So the other two things that I have is this particular sprite in here. I can technically display it anywhere on the screen. I'm showing it to you in here, but I could have easily just displayed it in here. Okay, so the difference between these two is actually where it's located, and I will just basically call that particular point, which is the origin or the sprite origin. That's what I'm going to call it, which is generally the top left corner of the sprite, and I'm just going to call it X0 and Y0. So I have X0 and Y0, and these are basically the origin of the sprite, okay, or sprite origin. I'm just going to call it sprite origin sprite. So these are the two dimensions. So I have X and Y for the pixel that is currently being displayed, and I have the X0, Y0 is just the sprite origin where it's displayed. So if you change the X0 and Y0, you'll be changing where that sprite is actually displayed on the screen. So we have an XR and YR. So let me show you how or what they are. Well, as the name implies, the R stands for relative. So they're X relative and Y relative. So let me show you how we actually compute it. So usually XR is X minus X0. Okay, so let's talk about this here, and YR equals Y minus Y0. So let's talk about how these are done. So when you actually take the X minus X0 or Y minus Y0, you're effectively doing the following. You're actually telling me, okay, I will have my axes, my X-axis in here, and I have my Y-axis in here. And that's basically what I have. So I have XR in here and YR in here. And it's called relative because now the two numbers I get, which is XR and YR, will be relative to this particular new coordinates. Technically, I will know the pixel location or the active pixel in reference to this particular origin. So basically, where I am within this sprite. So if I'm at 0, 0, I'm in here. If I am at 1, 0, that means I'm in here. 2, 0, I'm in here, and so forth. So these are really useful because it will tell me basically whether I am within the sprite or outside it. That's what's going to happen. So now that we know that what we have here on this particular figure, I also want to emphasize a couple of other metrics in here or measures. So H and HS, which is the horizontal size, basically how like the width of that particular sprite we have, whether it's 12 pixels, 20 pixels, whatever it is. And the VS is actually just the vertical size or the horizontal. So I'm just going to highlight them in here, or vertical size of the sprite, not the screen, just the sprite. And these are important. We're going to use them in the particular generation circuit in here. So now that we know all this information, let's dig deeper and just see how the actual generation circuit actually works. So here's the diagram in here, and the first couple of components I want to emphasize are here, which are just basically subtractors that implement these particular equations. So they take x and x0, y and y0, and they just generate the xr and yr. So now I have my relative coordinates within the particular sprite, where like if the pixel generate or if the pixel being sent to the VGA is here, I know its relative coordinates to the sprite basically origin. Okay, so now really the other components are basically just RAM, a multiplexer in here, and some sort of a circuit here. We're going to call it the decoding circuit. So let's see what the Sprite RAM is. Well, the Sprite RAM is just because I will have different shapes within that sprite. I don't care what that shape is, but I'll have it differently. So I'll have to store it somewhere. So I'm just going to store it in a RAM. You might be thinking, well, if it's a mouse pointer, doesn't really change, so why do we need a RAM? Well, you can definitely just do it with a Sprite Ram, but we're going to do it as a RAM so that the processor can change that figure if it wants to later. But anyway, it's just basically a storage location. Okay, so before I jump or dig more into that circuit, I just want to tell you how do we store that particular bitmap in here. So what I have is, let me just do that in green. I have 1 pixel, 2 pixel, 3 pixels, 4 pixels, and whatnot. So I have basically a two-dimensional pixel array in here. So how do I store these in a Sprite RAM? Well, as it turns out, you're going to take the first pixel in here and you're going to store it in the first row. So what you have is you have like 1 0 1 1 0, and really what you have is basically 12 bits in here because we have the R and the G and the B. So each row, so what I'm telling you here in the RAM is each row will contain an information for a single pixel, the red, the green, and the blue for the single pixel. Once you store that one, you're going to move to the next pixel in here, and that next pixel in here will be the second row, and then the third row, and then the fourth row, and then the fifth row. So basically that particular sprite or the RAM will be, well, let's compute the size. We know it's times 12 because each row will have 12 bits because the RGB have 12 bits. So how about basically the depth? This is basically width. How deep it should be? Well, it should be basically HS times VS, basically how many pixels we have, VS times HS. And that's how that RAM is. So what happens is the following. So the ultimate goal of this particular generation circuit is the following. It should either output whatever the pixel in here is, the pixel value from the RAM, or it should basically absolutely generate the chroma key. If you're outside the core or somewhere around here, let me change that color in here. So if you're around in here, for example, you should generate the chroma key, and generally that chroma key is 0. So let's put that 0 in here. Okay, so the ultimate goal in here, it's either to, if you are within that particular core, you should basically read it from the RAM. That's basically what this is telling me. And if you're outside it, whether you're here, 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 or here, you should just basically do the chroma key, which in our case, we're just using the 0, but it could be anything that we want. That's why I actually did that in green. Okay, so how do we decide that? Well, the multiplexer decides that, but what decides which one of them? Should I read the RAM basically, or should I be out? So what we have what we call an in-region circuit, and that in-region circuit just tells me if your global frame basically counter, which is X and Y, remember it's we have the pixels for the VGA is basically over there. If I am somewhere in the middle or within that particular sprite, that particular region will tell me I am in that. And how does it really work? It's really straightforward. It just basically says, okay, I know that what XR is and I know what YR is. So let's take a look in here. If XR and YR is the following. So if it's XR is between 0, which is this particular value, and H of S, and at the same time I have YR, which is between 0 and V of S, that means I am within that sprite core. That means you have to read that particular value from the RAM, not from the chroma key. And that's how that particular decoding circuit works. So that's how that particular sprite generation circuit actually works. It's really straightforward. So we have RAM, in-circuit generating circuit in here, and of course we have some sort of a multiplexer. So let me just talk a little bit about what am I doing in here with the XR and the YR in here. Basically I'm taking the XR and the YR and I'm using it as an address for the Sprite RAM. So let's dig a little bit deeper into that. So in here, what I did is I went ahead and I just basically took the mouse sprite in here and I'm showing you the information. Hopefully you get to see it. It's basically in here. If you see that, that's basically a mouse pointer. That's how I'm showing it here about that. So what I did is I'm just showing you all of the pixels. Of course, I expanded it for a reason that will become obvious shortly. So this one is 12 by 20. However, I expanded it to be 32 by 32, basically from 0 to 31, which is 32 by 32. And we'll see why shortly. But anyway, before I jump into that reason, let's see how we actually compute the address. So the address within the RAM, so remember, that pixel will be like, let me just draw that here. Like for example, let's assume that this is the RAM and that particular pixel will be the first one in here. Okay, the next pixel would be somewhere in here. So in order for me to figure out which row a specific pixel is, I need to use this particular equation. And the equation is really straightforward. It tells me how many rows, that's YR basically, which one of these numbers, how many rows did you pass, and we multiply by H of S, and H of S is basically the number of columns, actually, like the horizontal size. Okay, so for example, let's see the blue and red ones in here. For example, the blue tells me you are in row 2. That means you basically you pass 1, 2. So that's 2 times 32 in here. Okay, plus I have 0, 1, and 2. That's basically my X. So the YR is 2 and the XR is 2. That's basically for the blue. I have the XR and the YR and they're both 2. Okay, and that tells me on row number 66, so if you actually go in the RAM and you go to row number 66, you get that information, or you'll have the 444 in here, which is in hex. That's what you're going to read. If you go similarly, if you go to actually row number 67, as this particular equation tells me, you will actually read that particular 0, which is actually the chroma key. So if you think about it, I might have chroma key within that sprite, but that's beside the point. Okay, so that's how this works. If you take a look at it, this particular computation takes YR, HR, and XR and some H of S and just basically does a multiplication and an addition, which is not too much. But as it turns out, there's actually an easier way to do it without a multiplication and without an addition. So let me show you how we can do that. So the purpose of what I'm about to show you is to just reduce the computation and complexity a little bit so that to make the circuit a little bit faster. So what we're going to be doing is now we're going to restrict our H of S and V of S to be in powers of 2. This is why I expanded these two to 32 bits. So I'm saying, okay, let's restrict these to H of S will be 2 to the power H, basically it's a power of 2, and the V of S, or V of S, basically the vertex size will be 2 to the power V. So in this case here, I just basically chose 32 and 32 for the sake of simplicity. I could have basically said that this is 16 and this is 32. But for the sake of simplicity, let's just do 32 and 32. But we know that 32 is 2 to the power 5, so that means this little h is 5 and this little v here is 5. Anyhow, this is a restriction, and let's see how would that help us actually. So we're going to go back to the address equation in here, and I know that I have a multiplication and whatnot. But anyway, I know that h of s now is exactly 2 to the power h, regardless of what h is. So I'm just going to replace it by it. Okay, and now we take a look at that, and I know that y of r times 2 of h is really because I'm multiplying by 2 times 2 times 2 times 2 every single time. I'm just basically doing a left shift, and technically it's because it's to the power h, I'm doing a left shift by h. H, remember, is the number of bits necessary for the h of s, which is actually represent the x. And really, if you're doing that plus that, you really are just concatenating the y of r and x of r. This method is super smart in figuring out the address within the RAM. So if you think about it, the y of r has been shifted by the number of bits necessary for x of r. So let's and then you concatenate both numbers to get that address. So let's see, this particular blue tells me I have the y of r is 2 and the x of r is 2. And both of them is 5 bits. So I have 5 bits for the x of r and I have 5 bits of the y of r. So, and this is 2 and this is 2. And if you really concatenate these, you'll get that 66 in decimal. And the same goes in here, and you'll get that to the 67. Okay, so now I reduce that multiplication and addition to just concatenation of two numbers that I'm already generating. So going back to that particular figure in here, that's what I'm showing you in here. I'm showing you, hey, take the x of r, put it as the most, or the least significant bits, takes the y of r, and take them as the most significant bits, concatenate them. You have the address of where do you need to read it. So now you know that your pixel location is in here. You know the x of r and y of r. You technically also know which row you need to read from RAM to display that particular value.